Hello, so in my last two videos I talked how metric spaces include many of the spaces you see elsewhere in mathematics, and then I gave in a second video some more examples of metric spaces that are not necessarily normed vector spaces. Now I want to go over the very elementary questions and basic properties about metric spaces that you can talk about. The first thing from a categorical point of view would be to say when two spaces are exactly the same structurally. And the answer is what we call an isometry, which, as its name suggests, is a map between the two spaces which preserves the distances. So an isometry is a bijection map from x to y, such that if you take a pair of points in the domain and you look at their images in the target space, the distance between x and y is exactly the distance between fx and f of y. And because a metric space has no other structure than the metric, this tells us that up to a renaming of elements, they are exactly same objects. So isometry is probably, not probably, is exactly saying when two spaces are, to us, just the same objects. Now, a weaker notion would be that of a Lipschitz map between two spaces. So a Lipschitz map between two metric spaces would be some f from x going into y, such that for every pair that you take, so you want to look at f of x and you want to look at f of y, you want to look at their distance inside the metric space y, so d subscript y, and then you want to compare it to the distance in the x metric space of the points themselves. So if these were equal, you would get an isometry. But we make the assumption weaker, so we say that this is less than some L, which is called the Lipschitz constant, times that distance. So f is Lipschitz, we should say, just to be precise. Lipschitz was some mathematician. If there exists some universal L, such that this happens for every x, for every y. So that L does not depend on the choice of pair of points. Lipschitz maps are very important in metric geometry because, well, once you pass isometry, they are the closest to preserving some kind of structure. But actually between them there is the stronger notion of bi-Lipschitz. So in this case, so if you look at the definition of the Lipschitz map, a constant map will be actually a Lipschitz map because it crushes all the points to one point and crushes all the distances to zero. And that may not be desirable in many situations because it takes away all the geometry. Therefore, we look at bi-Lipschitz map, where you would require that there is one capital L and there is one little l, such that this time there is also a bound from below. So you want to have f mapping two points, but without stretching the distance too far. On the other hand, also not crushing them. So it's also bigger than distance xy. So that's the notion of bi-Lipschitz maps. Now, example, for instance, if I give is, we know 0 and 1 is an open interval, and we know that from topological point of view, it's the same as R1 because there is a continuous map with a continuous inverse map that takes 0, 1 onto R1. But you can see there cannot be any bi-Lipschitz map between them. So these spaces, these metric spaces, cannot be bi-Lipschitz equivalent. There isn't a bi-Lipschitz map between them. It can be seen from, for instance, saying that one set is finite, of finite diameter, the other one is infinite diameter. And that's where you see that metric structure is a bit stronger than topological structures. And the questions of when two metric spaces are Lipschitz equivalent is not actually an easy question. And if you remember, there was this Heisenberg group that I talked about, which is R3 with a new distance, which we call the Carnot distance. And from a metric point of view, it's very different from the usual R3 with its usual Euclidean distance, which comes from norm. And there is actually, it is true that no open neighborhood of this space is bi-Lipschitz equivalent to any other neighborhood of the other one. And proof of that is not completely obvious. So right here we can begin talking about research level questions, and that's one thing nice about metric spaces, because it's quite fast to begin thinking about very deep questions without too much background. Anyway, so such questions of when two spaces are equivalent or not, whether there is a bi-Lipschitz map between pieces of them or not, can be collected under the umbrella term of rigidity results, or say rigidity questions about spaces. Now, now this is how we compare two metric spaces. What can we say about just you have one metric space, and what kind of structure is on this space, and what objects can we talk about on this space? One of the intuitions that we have from the Euclidean spaces is that the distance between 2 points is equal to the length of the shortest path between them. Even when we move into the world of manifolds, if we have a connected manifold, again, the intrinsic distance is the shortest path from one point to another. This is not necessarily true. As we saw, we have finite metric spaces, so there is not even one curve connecting them, let alone having the shortest curve between them. But also, let's say you have xd, and let's call a curve to be a map from some compact interval into your space X that is continuous. Let's say a curve is a continuous map from AB into X. Continuous maps between metric spaces are well defined because the distance gives us a notion of convergence. And we can then say, we say that a curve like this gamma is rectifiable if its length is finite. The length of gamma is finite. But then the question is, what is length of gamma? And here is where you have to go beyond Euclidean spaces and manifolds. So in the Calc 2, Calc 3 version of length, to compute the length, what we do is you take derivative of gamma, which becomes the velocity of the curve. It is a vector, so you take its norm, so it's only the speed of the curve. You do dt, and you integrate from a to b, and that's your length. But this will not work in the context of metric spaces in so many levels. Number one, there is no way you can talk about derivative. Derivative is very closely linked to the notion of linear structure. So to compute derivative, remember, you subtract and then you divide, you form this difference quotient and you take limit. So in a general metric space, you have no notion of saying gamma of t plus h minus gamma of t. It has just no meaning. And that's why this approach will fail. However, there is another notion of how to compute length of the curve, which sometimes we see in early analysis books, but we kind of do not appreciate the real significance of it. And that is, we call length of gamma to be the supremum of summation of length of gamma ti plus 1 from gamma ti, and where I ranges from, say, 0 to n, and supremum over all partitions of the unit in this interval. So you want to have a equal t0, and then there is t1, and then so on, and then there is tn, and then there is tn plus 1, which is equal to your b. So the picture that may remind you of how this was computed is, so this is gamma of initial point, this is gamma of last point, and then you put some finite collection of intervals corresponding to discrete number of times. So this is your object at time t1, this is your object at t2, and then you add the length of these line segments, because when you talk about distance of one point from the next point, it's in Euclidean space, it's exactly this distance. And now you're adding all these distances, then you take supremum over all partitions, and so you add more and more of these finite points, you get a finer and finer mesh. And so under some conditions, if your curve is actually C1, so that this notion of length makes sense, you can prove that this also converges to that quantity. So they produce the same quantity. However, notice this notion requires no derivative. It only requires this notion of distance. Therefore, here I was thinking like I'm in R2, but even if you are in a general metric space, this does make sense. So the notion of distance is there, summation, you're adding some real numbers, and definitely supremum over partitions, which happen in just the interval. So sometimes, and it is important to know that your metric space is such that for every pair of points, in fact, there is some curve connecting them, and such that its length, in this sense, is actually equal to the distance. So if for every point, every pair of points, you can find a shortest path between them, you call these spaces geodesic spaces. And they of course, are an important class of metric spaces. So you can still talk about length of curves in a metric space, and go over all the examples of metric spaces I have ever given you, and consider what curves and length of curves would look like in those spaces. So what else? So on one metric space, so we can talk about curves and geodesics. What else can we talk about on a given metric space? And this one is more surprising. When you are given a metric space, just using this metric, you can construct Hausdorff measures on them. And we will go over these in detail. These Hausdorff measures are generalizations of exactly the length and area and volume. So Hausdorff measure H2 is computing area of a metric space if it is really two-dimensional in some sense. H3 computes its volume if it is in fact a three-dimensional space, and so on. And of course, this gives us a notion of Hausdorff dimension. And there are other notions of dimensions as well, which we can talk about on a fixed metric space. And once you have a notion of measure, you can also talk about integrals, because integration is nothing but measures applied to characteristic functions. And okay, so we will see that these are actually quite non-trivial, and it's quite surprising that just having the distance function you can do this much on an abstract metric space. So then I want to finish by some properties of metric spaces. So a metric space may or may not have these properties. A metric space is a topological space, so in particular we can talk about its compactness, we can talk about its local compactness, we can talk about whether it's separable or not, which is when you have a countable set which is dense inside your set. So these are particularly nice spaces that we love, and this separability is basically saying that the spaces are not too big, and lots of analysis on metric spaces are more easily done on separable spaces. We can ask about completeness of metric spaces, whether the limits that should exist do exist in your space. And so these are some immediate things that follow from just the notion of distance on metric spaces. But once we begin our treatment of Hausdorff measures, we will follow by notions of rectifiable spaces, and we will talk about later we will add a measure to our space. So we will have a metric space plus a measure on our space, and these are called metric measure spaces, which is just another beautiful universe of objects with a lot of analysis. Actually, when they say analysis on metric spaces, they implicitly mean analysis on a metric measure space, because without the measure you cannot talk about Sobolev spaces, and there isn't much analysis that you can do, except for the notions of rectifiability, which do not require measures other than the Hausdorff measure. Okay, so hopefully this again adds to your motivation to follow with metric spaces, and hope to see you in future video. Please subscribe and tell your friends about my channel. That's the best way you can support me, and Hausdorff measures are upcoming very soon.